The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. As we approach the year 2020, there's no doubt that we have obtained a tremendous amount of hindsight. I am terrible at euphemisms, and as a little girl, I always believed that everybody in the world would obtain all the hindsight they ever could obtain by the year 2020. On some level, that is kind of true, especially when it applies to math and science. Hindsight is pretty amazing, but it's also a bit overwhelming. Specifically, let's talk about math and all of the things that we have learned up to this point in the world. It's a lot. It's tremendous. Could you imagine if one person decided to take all the information, everything we know, everything that's ever been written about mathematics and put it in one book? How big would that book be? It would be huge. It would be bigger than huge. It would be endless because even today, new theories are being made. New achievements are being obtained. Conveniently, we have the internet that we can just post all this information on. But could you imagine putting it all in one book? Or could you imagine putting it on 13 scrolls? Could you imagine how big those scrolls would be? Around 300 BCE, Euclid wrote his book, The Elements. Many think that this was Euclid's book, that he came up with everything that is in the elements. And though he did, and though he was a tremendously brilliant mathematician, much of his work came from the condensing of mathematics that had been evolving for hundreds of years. Hundreds of years of applications and theories contributed to the incredible and amazing body of work that even today still serves our students in school. Thus, Euclid stood on the shoulders of giants. There were many, many, many mathematicians long before his existence on the planet that had been thinking and developing and coming up with new theories that at that time were insanely advanced. But today, they are truly foundational. In 600 BCE, Thales of Miletus is it Miletus? I don't know. Anyhow, in 600 BCE, Thales, who founded the Ionian school, was one of the first to define numbers as a system of units. Also, he had propositions in geometry that were some of the very, very first presented in the form of a proof. For anybody who's had to do proofs, you know why that's not easy. Thales was actually the forefather in this process. Also around this time, around 570 BCE, Pythagoras began to work upon Thales' proofs. Rightly so, because Pythagoras was Thales' student. Pythagoras was a really brilliant man, a little crazy, but nonetheless brilliant. And though his teachings were by word of mouth, Philolaus of Crotona and Archytas preserved them. We all know Pythagoras as the genius behind the process of finding the hypotenuse by adding the square of one side to the square of the other. Yep, that's Pythagoras. So about 100 years after Pythagoras, Socrates came onto the scene. He lived a really long life. He lived to the age of 71, which at that time is pretty amazing. His method of logic and processing became known as the Socratic method, and it was a cornerstone to understanding geometrical analyses and proofs. A contemporary of Socrates was Philolaus of Crotona. I mentioned him earlier. Philolaus was mostly a philosopher, but he was also one of the first Pythagoreans to write the treatise on Pythagoras' teachings. Around 450 BCE, Hippocrates emerged onto the mathematics scene. He was an unsuccessful merchant who became a Pythagorean philosopher. Hippocrates was one of the first mathematicians to use reduction ad absurdum, which is actually a method of reduction. In using reduction, Hippocrates introduced the process of reducing one theorem to another, more straightforward theorem. This reduction method reverses the process by using that proof to clarify the original proposition. In other words, reduction ad absurdum is a method of argument that attempts to 1. Disprove a theorem by showing that the alternative leads to an absurd conclusion, or 2. Prove a theorem by showing that if it were not true, the outcome would be illogical. Around 428 BCE, Plato came onto the scene. Plato was a student of Socrates. The Socratic method actually enthused Plato's logic with an exposition, and this contributed to Euclid's axiomatic deductive proofs. If you've done proofing, you'll know exactly what I'm talking about. In 458 BCE, Archytas of Tarentum began his legacy as a Pythagorean philosopher, philanthropist, public official, general, educator, and mathematician. That's incredible. He lived for 80 years. This guy was brilliant, and he basically did everything. He could probably even take up knitting, even though it hadn't even been invented at that time, because he was that amazing. Archytas had theories that were foundational to projective geometry and number theory. Archytas used mechanics to describe geometry, and this in and of itself was groundbreaking because he actually took concepts in math and made those concepts tangible to his students. All of his work is included in Book 8 of Euclid's Elements if you're interested in reading it. Around 390 BCE, Eudoxus was born. Eudoxus's contributions, that's a mouthful, Eudoxus's contributions to science and geometry were huge because they aided the future of mathematical astronomy. He introduced the astronomical globe and was one of the first Greek scholars to present an accurate portraiture of constellations in planetary movements. As a mathematician, Eudoxus augmented Antiphon's method of exhaustion, which is a method that's currently foundational to integral calculus. In 334 BCE, Aristotle, a student of Plato, included all of his mathematical applications into physics and called for the separation of arithmetic and geometry. His most significant application came from his definition of continuity. Finally, around 300 BCE, Euclid wrote the Elements. Using the work from these tremendous mathematicians, he wrote a tome out of all of these theories and then added some of his own theories and mathematical developments. So it wasn't really a reference book. Instead, the Elements was a textbook for students to use. So it doesn't cover everything about math and everything that every mathematician knew at that time, but rather it taught the foundations in the basics of mathematics. Euclid's Elements was one of his most profound works, with theories that still apply today. This body of work includes 13 books and 468 mathematical propositions that cover topics that include geometry, algebra, proportions, abstract proportions, number theory, incommensurables, and solids. Euclid wrote Elements in 3 sections that included plane geometry, ratio, proportions, and spatial geometry. Wow. It sounds like a lot. It was a lot, and he wrote it all down on scrolls. Today, it's one of the most published books in the world. Yep. There are websites dedicated to the Elements, and there are a multitude of books that discuss Euclid's Elements. There is even an interactive website called Burns Euclid, which is a reproduction of Oliver Burns' work from 1847. You can find it at a website that is called C, as in the letter C, 82, that's c82.net/Euclid. Today, Euclid's Elements represents the power of shared knowledge and the power of the written word. Knowledge is power, only when it's shared. Euclid's Elements made all of the mathematics that he knew up to that point cohesive. It brought so many different concepts together and taught millions the foundations of mathematics and the wonder of numbers. And so, to misuse another euphemism, I just want to say that there is power in numbers. Lots of numbers. Big numbers, little numbers, real numbers, imaginary numbers. There is power in numbers. I'm Gabrielle Burchak. This podcast has been brought to you by caffeine. Delicious, wonderful nectar of the gods caffeine. Coffee, tea, coffee candy, you name it. I love it. Thank you for listening to Math Science History. If you are interested in reading more about the history of math and science, please come visit me at mathsciencehistory.com. And while you are there, if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Until next week, carpe diem.